The intermediate value theorem is a great example of one of the uses of continuity that kind of builds on it and shows you an actual application for some of the things that you learned about with continuity and limits previously. So I recently went over the intermediate value theorem in one of my live streams, which I'm doing every Monday night at 5 Pacific, and I thought you might get some use out of this, so I wanted to show it to you. I do go over topics like this in a lot more detail also in my complete Calculus 1 package. If you haven't checked that out already, there is a link down in the description below where you can get more information on that and go get that right now. It is available for instant download, so if you want to go get yourself a copy of that and start using it right away, it should be a huge help to you. But without further ado, let's go ahead and jump on into the intermediate value theorem. Basically what the intermediate value theorem says is if we have some function f, and I'm going to just kind of tell you exactly what the theorem says to start, and then I'll get into explaining kind of visually what this looks like and what it actually means, because I know a lot of times when you're reading theorems or different things in calculus, it kind of sounds like nonsense. So I want to be sure to kind of explain what this really actually means in English instead of in math. But what the theorem actually says is we have some function f, which is continuous on a closed interval from a to b, and we have some number n, which is any number between f of a and f of b. We need to make sure that f of a does not equal f of b for this to work. Then, based on knowing that this stuff is true, there must exist a number c in the open interval a to b such that f of c equals n. So what does this mean? Well, really all this is saying is we have some continuous function f, which is continuous on an interval. It doesn't have to be continuous everywhere, but we need to make sure that it is continuous on some closed interval, where let's kind of actually show what this looks like graphically. That's probably going to be the easiest way to make sense of this. All right, so we have our x and y axis here, and let's just say we have some function which we know. So let's kind of think about what conditions we have here. We have some function that is continuous on some closed interval from a to b. So let's just say that we have some interval like this from a to b, and our function is continuous on the closed interval. So we know it's going to be continuous all the way up through those points, basically. Let's just say something like this. Actually, not quite like that. Let's go like this. Let's just take this for example. So this is a function that is continuous over this whole closed interval from a to b. And we have some number n, which is between f of a and f of b. Well, f of a and f of b is just saying whatever output you get when you plug in a and b into this function. Or in other words, the y value of whatever your function is at these 2 points a and b. So basically this right here is f of a, and this right here is f of b. It's just the point that lies on this function at these x values that we're looking at. And then we have some number n, which is between them. So we know basically that n has to be somewhere between there and there. So it could be anywhere in here. We know, based on the intermediate value theorem, that there must exist some number c between a and b. So then there's some other number c, which is between here and here. So let's just say right there, for example. Or, you know, it kind of works the other way. So we would need to pick our n first. So let's just say our n is here, anywhere between these 2 points on the y-axis, basically. And we know that there has to be some number c between a and b, where if we look at our function at that x value of x equals c, we can get the output of n. So basically what this is saying is if we know our function's continuous, we know that our y value of our function at these endpoints here of a and b are not equal to each other. Basically, that's saying there's a possibility to pick some number between those two outputs, those two y values. And since we know the function is continuous, no matter what n we pick between here and here, there's some x value that basically we can plug that x value into our function to get this n as an output. So in this case, you can see that it would be right about here. We can plug this c value in here into our function, and that'll give us n as an output. That's not a very straight line, but hopefully you can kind of get the idea there. No matter what n we pick between f of a and f of b, there's gonna be some c between these a and b values where we can get that n as an output. No matter where we pick our n, let's say we pick an n here, we're going to be able to get some c value between a and b that we plug into the function and get that as an output. So that's really what the intermediate value theorem is telling us. And that's all built on and contingent on the fact that our function is continuous over this whole interval of a to b. If it's not continuous, then it's not going to really be applicable. The intermediate value theorem won't really tell us anything. So we need a continuous function. So why is this important? Well, this has some valuable information that we can gather about a function that we know is continuous on some closed interval. So for example, I have a example problem here that kind of shows you how this is helpful or what you can do with it. Let's say we have this example here. We need to use the intermediate value theorem to show that there is a root of the given equation in the specified interval. So basically we have this equation here, and we need to show that there's a root, or in other words, there's a solution to this equation. There is a point between this interval here, between 0 and 1, x between 0 and 1. There must be a point where the cube root of x equals 1 minus x. Well, to use the intermediate value theorem, what we need to do is kind of think of a couple different adjustments that we can kind of make to this problem. First of all, a root kind of implies that there's a point where we have a function that equals 0, right? We don't really have anything equal to 0 here. So what we probably want to do is basically add or subtract everything over to one side of the equation. So let's just say we will subtract the cube root of x from both sides, and we'll get 0 equals 1 minus x minus the cube root of x. So the reason why we wanted to do that is now we can think of this right side of our equation here as our function. So we have some function f of x, which equals 1 minus x minus the cube root of x. And we want to find a root of this function between x equals 0 and x equals 1. So where does the intermediate value theorem come into play? Well, we need to first of all make sure that this function is continuous on this whole interval from 0 to 1, which really all three of these pieces of this function, 1, negative x, and negative cube root of x, those are all continuous everywhere. So as a result, this entire function is going to be continuous everywhere. Cube roots are fine to take. It's fine to take the cube root of a negative number, so we're not going to get any issues here with taking a cube root of x. But even if that were an issue, 0 to 1 is obviously not. There's no negative numbers in there. So everything between 0 and 1, this whole function is continuous. There are ways that we could prove that, but I'm not going to get into that here just because this problem specifically tells us to use the intermediate value theorem. As a result, I think it's reasonable to assume that this function is continuous based on how the problem is telling us to solve it, because the intermediate value theorem needs the function to be continuous in order to actually use it. So let's just go ahead and assume that this is continuous within this interval, at least. Basically, let's kind of think about this piece by piece here. Thinking about what the intermediate value theorem tells us. It tells us that we have a function, in this case, that is going to be continuous on the interval of 0 to 1. And we want to look at, basically, kind of looking back here to the intermediate value theorem, we want to look at basically the endpoints of that interval. So f of a and f of b. So if we think about, in this case, f of a, which is 0, and f of b, which is 1, we want to figure out what these two values are, because intermediate value theorem is going to tell us that there has to be a place on this function, this continuous function, where we can basically obtain any output between whatever these two outputs are, and it's between the inputs of 0 and 1. So let's just figure out first what f of 0 and f of 1 are. So f of 0 would just be what we get from plugging in 0 into this function. So 1 minus 0 minus the cube root of 0, which the cube root of 0 is 0. So we're going to get 1 minus 0 minus 0, which is 1. Okay. And then f of 1 is just going to be 1 minus 1 minus the cube root of 1, which the cube root of 1 is 1. So we have 1 minus 1 minus 1, which is -1. So basically what we know is, for any possible number we pick between -1 and +1, there has to be some x value that we could plug it into this function f of x in order to get that output out that we pick. Well, since we're trying to figure out, is there a place where this function equals 0, we can use the intermediate value theorem to say, well, yes, there must be a place, there must be an x value that we can plug into this function to get 0, because 0 is between -1 and 1. So as a result, we know that there has to be a root between this interval here. We don't necessarily need to figure out what it is. This problem does not ask us to do that, but we know that that root has to exist. We know that there has to be an x value where we can actually get 0 as an output, since it's between -1 and 1, and since we know our function is continuous on the interval 0 to 1. Well, I hope you found that video helpful. If you did, please be sure to hit that like button down below. That's a huge help to me and my channel, so I can keep making more videos like this for you. And like I said, if you want to keep building on this stuff, go check out my complete Calculus 1 package. There is a link down in the description below where you can learn more about that. And I have also made some other videos related to the intermediate value theorem, so if you want to check those out, go ahead and click on one of those over there. Thanks, and see you next time.